Hello, my name is Somajit. I am going to talk about how we can use machine learning to detect e-commerce fraud. Opportunity evaluation. The problem. Online fraud costs banks and merchants billions annually. It erodes customer confidence, leading to significant administrative overhead from chargebacks and investigations. Why ML is the solution? Machine learning, specifically classification models, can discern complex evolving fraud patterns with greater precision and recall than traditional methods. This capability is crucial for identifying fraudulent transactions in real time within vast datasets. Driven by stakeholder needs, all key stakeholders in the financial institutions, in the payment processors, and merchants are highly motivated to mitigate fraud. Reducing fraud rates directly contributes to customer loyalty, improved operational efficiency, and substantial cost savings across the e-commerce ecosystem. Defining the scope and success matrix. Defining the problem. Merchants need to instantaneously distinguish between genuine and fraudulent transactions. Our primary objective is to reduce the fraud rate by 50% while maintaining an industry-leading false positive rate below 1%, ensuring minimal disruption to legitimate customer transactions. Key question: which features are the strongest predictors of fraud? How do we optimize between fraud detection accuracy and customer experience? Defining success. Our success will be measured by both model performance and tangible business impact. We aim for a true positive rate more than 0.90 for fraudulent transactions and in a false positive rate of less than 0.01 for genuine transactions. Identifying relevant factors for fraud detection. Transaction attributes. It includes amount, time, merchant category code, device ID, geolocation, and transaction velocity. Provide initial context. User behavior. Patterns such as purchase frequency, average transaction size, and historical fraud levels offer crucial insights into legitimate versus suspicious activities. External signals and network information. IP reputation, velocity metrics, blacklisted entities, and graph features like linking users, devices, cards, and merchants will be leveraged to detect complex fraud rings. Developing and testing our ML approach. Solution concept. Our core model will be a supervised classification system utilizing ensemble methods like XGBoost, trained on meticulously engineered features derived from transactional data. We'll also prototype with graph neural network to uncover intricate relational pattern between entities. The solution will be deployed as a real-time scoring API integrated seamlessly into payment gateways, designed to achieve sub 100 millisecond latency for immediate transaction decisions. Iterative experimentation and validation. Hypothesis A. We hypothesize that an ensemble model on basic features will improve fraud recall by 10%. We will experiment by comparing baseline logistic regression with XGBoost using ROC curves, measuring AUC, ROC, and recall at a fixed false positive rate. Hypothesis B. Graph feature enhancement. We anticipate that augmenting our dataset with graph-derived features will further enhance the detection of organized fraud rings. Robust data collection and evaluation. To ensure real-world applicability, we will employ rolling window cross-validation, mimicking live deployment scenarios. Crucially, we will monitor online metrics such as actual fraud cases and false declines during a controlled pilot phase before a full-scale rollout. ML system design. Strategic architectural designs. Cloud versus edge. Obviously, we will prefer cloud-based inference. Given the stringent latency and security requirements of payment gateways, all model inference will be cloud-based. This ensures centralized control, scalability, and robust security for sensitive transaction data. Online versus batch. Purely online prediction. Fraud decisions demand instantaneous responses. Each incoming in transaction will undergo real-time online prediction to approve or decline instantly, preventing fraudulent charges before they occur. Online versus offline learning. Offline batch retraining will be used here. To maintain model stability and adapt to evolving fraud patterns, retraining will occur nightly via offline batch processing using the previous day's leveled data. This approach also integrates the model drift detection for continuous optimization In potential production risk, training serving skew. This occurs when feature pipelines differ between model training and real-time serving, leading to degraded performance. We will mitigate this by implementing a unified feature store and conducting rigorous end-to-end testing across the entire data pipeline to ensure consistency. Latency constraint in the high API latency during peak transaction loads can severely impact user experience and transactional approval rates. Our strategy includes leveraging auto-scaling for computational resources and implementing cache pre-warming techniques to ensure sub 100 millisecond response times even under heavy traffic. Data drift and concentrate. Shifts in input data distribution. Data drift or changes in the underlying definition of fraud concentrate can reduce model accuracy over time. We will deploy continuous drift detection mechanism and implement an automated model retraining cycles. Additionally, monitoring the false positive will help adjust the model thresholds proactively. Regulatory compliance adherence to the regulations like GDPR and PCI DSS is paramount for data protection and privacy. Our solution will incorporate robust data anonymization techniques, maintain comprehensive audit logs for transparency, and prioritize interpretable models to meet regulatory scrutiny and build trust. Thank you. Thank you for your time.